Okay, so it is um, my great pleasure to be here, and thank you so much for joining this event, and thank you for the invitation and for the opportunity to talk about what I'm interested in, and yeah, let's get started. Okay, okay, just for those of you uh who meet me here for the first time. So let me introduce myself. So I did my bachelor's in industrial engineering here at POSTECH, and I did my PhD in some joint program between mathematics, computer science, and business school. And the program is called Algorithms, Combinatorics, and Optimization. And when I was an undergrad student, I was really interested in like theoretical aspects of optimization algorithms, and that's how I ended up studying this major. And after my PhD, I did my postdoc at the Discrete Mathematics group at on research institution in Daejeon, and I was at KAIST for the last 3 years at the ISE department, and then I recently moved to the math department at SNU last semester. Okay. So here are some topics that I'm interested in for research. So I started my career as on integer programming and combinatorial optimization, which is called discrete optimization in at large. And uh, but after joining KAIST, I also got interested in continuous optimization and stochastic optimization. And more recently, I have worked on optimization algorithms for machine learning problems, including multi-embedded and reinforcement learning. Okay. Okay. Uh, One advertisement. I think it's a good place to advertise this event. So we are starting on annual workshop series on optimization theory and algorithms, and it's held by KIAS, which stands for Korea Institute of Advanced Sciences, and the dates are fixed. So it's gonna be in May, from 26th to 29th, and it will be held in KIAS Seoul campus, which is right next to KAIST Seoul campus. And here are the list of confirmed speakers, and we'll have about 15 to 20 speakers. So we're gonna invite more people, but we have already, secured these great speakers for the workshop. So including, Shantanu Day, Georgia Tech, and Jim Luque from University of Wisconsin Medicine, Melvin Sim from National University of Singapore, and others. Okay. So please join this event. And I think we were having this first edition of the workshop, and I hope that we can, encourage, lots of interactions and activities between multiple places for optimization and algorithms in general. Okay. All right. So today's title is discrete optimization via continuous optimization methods. I think the general theme of this event is on the future of optimization for AI. The reason why I chose this topic uh, was that we've seen lots of works on GPU-based acceleration for optimization algorithms, like these things. So I guess for those of you who are working on like combinatorial problems, you might have heard of this algorithm called primordial hybrid gradient, developed for linear programming. So we've been using simplex method and barrier method for linear programming, but people are trying to get new algorithm, which is more efficient than the first two, which is this primordial hybrid gradient. The feature is that it can be accelerated via GPU, so you can parallelize implementations. And now, like if you use GPU implementation, it's gonna be very fast. And also ADMM can be also implemented in a parallel fashion within GPUs, and also interior point method, barrier method, and operator splittings. All these continuous optimization techniques are developed within GPUs, and they are already implemented in various ways for machine learning and artificial intelligence. And the question is that, can you use these techniques for discrete optimization or integer programming methods? Okay. So I have a friend from Ohio State, and I met him like a few weeks ago, and he was telling me that he had a recent paper on some parallel method for nonlinear integer programming. And as soon as he uploaded the paper to archive, he received like direct emails from like 5 companies on integer programming solvers. And like these software companies are very interested in, parallelizing algorithms, because that's at the core of, improving the computational complexity of their solvers. So this is the main question. And I think one possible approach to tackling this question is to borrow these technologies for continuous optimization when it comes to solving discrete optimization problems. Okay. But perhaps what I will be presenting today might not directly tackling this question. Maybe something that I talk about might be quite far from answering this question, but I just want to introduce and explain some important works and techniques that bridges discrete and continuous optimization. Okay. So here's the list of topics that I'll be presenting. So in the morning, we will have the first 2 lectures. So the first 2 lectures are rather classical results, but they are very important. But the last 2 topics are something more related to machine learning problems. And I think that if you see the titles, like I will talk about these problems like in discrete optimization, and I'll be explaining things in terms of how a continuous method can be applied for solving these discrete problems. Thank you. All right. Feel free to interrupt me if you have any questions. Okay. Right. So the first lecture is on semi-definite programming for maximum cut and binary quadratic maximization. Okay. And so SDP here stands for semi-definite programming. Okay, here's the outline. So I'll define this maximum cut problem, and I'll show you some easy algorithms. And then I'll move on to the best possible algorithm, best known algorithm for solving max cut. And then I'll explain that the same algorithm can be extended to a more general class of problems, which is called the binary convex quadratic maximization. Okay. So, graph cut. So we are given a graph with vertex set V and edge set E, and a partition of the vertex set V is given by these 2 sets, V1 and V2, whose union is the original set V, and they don't overlap. Okay. Right. And a cut, which will be of main interest for today, is a set of edges that are crossing this partition. So if you see this example, we have this graph on 5 vertices, and this red vertices and black vertices give you a partition. And then if you collect these green edges, they are crossing the partition, which means that if you have an edge, it has one end in red and the other end in black. Okay, so right. And the question is you are given a graph, what is the maximum number of edges in a cut? Okay, so you want to find the partition so that the corresponding crossing edges, the number of crossing edges can be maximized. Okay, that is the question. Okay. Well, so, but the thing is that there are possibly, exponentially many partitions. So going over each partition one at a time might take an exponential time. So that's not so kind of, the naive enumeration is inefficient. So can you do something better than this? So let me show you an easy algorithm, okay, which is randomized. So the algorithm is very simple. So what you do is the following. So you go through one vertex at a time, and you flip a coin, and you mark that vertex with probability 1/2. Okay? And then you collect the set of marked vertices, and then you give the name of V1 to that set. Okay? Then V2 will be the set of vertices that are not marked. Okay? And it shows that if you look at the cut edges given by this random partition, the number of edges in that partition, in that cut, is at least 1/2 of the maximum number of edges. Okay? And we say that because of this, inequality, we say that this algorithm is 1/2 approximation for max cut. Okay? Great. So let me give you an easy argument for this theorem. So what is the expected number of edges in the cut? Well, the expectation, by the linearity of expectation, you just kind of go through each edge, and then you compute the probability of this edge belonging to this cut. Okay. What is the probability? That is exactly one of these two end vertices, U and V, exactly one of them is marked. Okay, that's how one vertex belongs to this V1 and the other one belongs to V2. Okay, is this clear? Okay, right. Then what is the probability? Well, it is not too difficult. Well, I guess one is U is marked and V is not, which is probability of 1/2, so 1/4. And you do the same thing for V and U. So you have 1/2 for this probability. So essentially, I think this has to be equal. So here this probability term equals 1/2. So the right-hand side is equal to 1/2 times the number of edges. And the optimal number, or the maximum number of edges in a cut, has to be at most the number of edges in total. So this is the argument. Okay. So, enumerating all possible cuts can be inefficient, but there's a very simple algorithm that admits, that gives you, the 0.5 approximation of the maximum possible number of edges in a cut. But you might not be happy with this expected performance. So it means that the number of edges can be, smaller than the right-hand side. although the in expectation, the number is greater than or equal to the right-hand side. Um, in fact, there's a deterministic algorithm which guarantees the same performance with probability of 1. So that is done by this. So what you do is the following. So you order and label the vertices from 1 to n. Okay. And then you pick vertex 1 at a time. Let's say you have picked the first j minus 1 vertices. Now it's the time to look at vertex j. Okay. And what you do is the following. So ej, so here you have vertices from 1 to j minus 1. Now you look at vertex j. And ej is a set of edges that are connecting this vertex j and the vertices that are already picked. Okay. And here, my assumption is that um, this set is divided into two, V1 and V2. Okay, currently this set of vertices contains the first j minus 1 vertices, and I assume that they are partitioned into V1 and V2. Okay. Then here, if you look at the current setting, now you count the number of edges connecting V1 and J, and edges connecting V2 and J. Okay? And you assign J to, let's say, uh, V2 if the number of edges connecting J, V1. So depending on, so what you want to do is you want to create the maximum possible crossing edges. Okay, so if you move J to V2, then you're adding 2 edges to the cut. But if you move J to V1, then this edge will be the crossing edge. Okay, so you assign J to either V1 or V2 depending on the number of edges you are newly creating, and that is the greedy choice. Okay. So you add, right. You compare the number of edges that you newly create by adding J to the first set and the second set, and you compare these two numbers, and depending on you assign J to one of these two sets. And it also guarantees 1/2 approximation of the problem. Okay. And the proof is also not difficult. So again, and by the definition of these edges, edge sets E1 through En, they give you a partition of the edge set. They don't overlap. And so after running this algorithm, now you look at the final V1 and V2s. Okay, the number of crossing edges by this partition can be decomposed in terms of these edge sets. And by our greedy choice of V1, you can see that the edges crossing contributed by this edge set EJ, then is half of the total edges in EJ. That's you can argue. And that's how you prove that the number of total edges crossing is at least half of the maximum number. Okay. So this is good. So by the way, I guess I had to mention that this problem is NP hard. So it means that it's hard to expect polynomial time algorithm for solving or producing the exact optimal cut. But we have presented a very simple 1/2 approximation algorithm randomized. And we also explained that there's um, a simple greedy algorithm that also guarantees 1/2 approximation. Okay. Now the question is, can we do better than this? Okay. And this is actually the main topic for lecture 1. And in fact, what we will use is something called semi-definite programming, which is an important class of convex programming problems. Okay, and these people, shown that SDP can be used to solve or improve the performance guarantees for max cut, which I will be explaining now. Okay, and in fact, max cut can be formulated by the following quadratic integer programming. Okay. So let's look at this formulation. So each vertex is labeled by -1 or 1. Okay. So essentially, each vertex is given 2 choices. And now, after assigning these values to these vertices, you collect vertices with -1 labels and collect the other vertices. That naturally gives you a partition. And if you look at this objective, it counts the number of edges crossing this natural partition. Okay, why is that? Well, so here, if XU and XV get the same labels, then the product will be +1. Okay, so the product of -1 and -1 is 1, and the product of 1 and 1 is also 1. In which case, this value will be 0. Okay, but if these 2 vertices get different labels, then the product will be -1. So this term in the parentheses will be +1, or +2 actually. So it actually, the sum, it counts the number of edges whose ends get different labels, which is essentially the number of edges crossing the partition, even by this distinct this -1, 1 labels. Okay, is this clear? Okay, so you have binary variables, but the objective is quadratic. Okay, so the degree is 2 because due to this product terms. Okay, and this is called the Ising model in statistical physics. And well, I guess the people in this community is more interested in the optimum value of this problem under some kind of different statistical models. But we, optimizers, are interested in how to solve this problem. Anyways, so we have this formulation, and what I will do, okay, sorry. So, in general, dealing with these binary variables is hard, especially when you have a nonlinear objective like this. Okay, so instead of working over these integer variables, you might replace a condition by this polynomial equation. Okay, so x having these binary labels is equivalent to the xv square is 1. Okay, now everything is continuous. Okay, you have even the objective is a quadratic function, and the constraint is a polynomial constraint. Okay, so it has become polynomial optimization problem. So what you do is the following. So let's take this vector x that consists of my binary variables. And what you do is to take a matrix X, capital X, which is given by the outer product of xn itself. Okay? So it's going to be something like x11, x12, x13, x1n, and all the way up to x11n and xnn. Okay? And I know that the diagonal entries have values 1. Okay? And this matrix is symmetric. And I know that this matrix is of rank 1. Okay? Because I'm taking the outer product of the same, outer product of two matrices. And this is positive semi-definite just because for any V in Rn, V transpose capital XV equals V transpose X squared, which is non-negative. So this is on positive semi-definite matrix. So essentially, the original, binary quadratic optimization problem for max cut is equivalent to this problem formulation, where now I have all variables are in terms of this matrix capital X. Okay, but the condition is that its diagonal entries have values 1, and it is of rank 1, and the matrix is positive semi-definite. Okay. But the thing is that the constraint imposing that its rank is 1 is non-convex. That is because, let's say you are taking X transpose and Y transpose. So these are two positive semi-definite matrices. And if you take the convex combination of these two, if as soon as lambda is strictly between 0 and 1, it has rank 2. Okay, so taking convex combinations do not preserve this rank 1 condition, and it means that the constraint is non-convex. Okay. So, but a common approach for this kind of problems is to take out the non-convex constraint, and you look at this problem. Now, right now, I have the constraint saying that its diagonal entries having values 1, and the matrix is positive semi-definite. Okay, and it is a relaxation if you are familiar with optimization terminologies, meaning that you are looking at a larger set of possible solutions because you have removed a constraint. Okay, and it's called and more precisely, it's called a semi-definite programming relaxation, because this problem, if you look at it, it's an instance of semi-definite programs. Okay, so you have problem objectives and constraints are written in terms of these matrix variables, and I'm imposing the condition that this matrix is positive semi-definite. Okay, so this is a semi-definite program. Okay. And also, a semi-definite program is known as convex minimization problem, for which we have on polynomial time algorithms like interior point methods or the ellipsoid methods. Okay, so as soon as you have this semi-definite programming relaxation, theoretically there's an polynomial time algorithm for solving it. Okay. Okay. So if you are just interested in the computational complexity of this problem class, then you are okay. You are happy. Okay. Any questions so far? Yeah, so it is a relaxation because let's say you solve this and let's say you get an optimal solution X star, but it doesn't have to have rank 1. So it doesn't translate to the original problem. If you had a rank 1 matrix as an optimal solution, then it'll correspond to a cut. But if that's not the case, then you are not getting the max score. Yeah, so that is a possible approach, but dealing with this rank 1 constraint afterward is a difficult approach. So instead of doing that, I will explain a randomized rounding algorithm. So you have an optimal solution next top, and instead of directly working over this rank 1 constraint, I will show you how to round this, how to get a random partition of the vertices using this matrix X star. Okay, and that is actually the key contribution of this paper. Okay, any other question? Yeah.
So matrix X is the variable.
Right.
And then we have to satisfy that X is positive semi-identity.
Right.
We have to explicitly express that constraint.
Okay. So it's equivalent to saying that this matrix belongs to something called the positive semi-definite cone. Yeah. Positive semi-definite cone. And if you remember how the ellipsoid algorithm works, it's about separating your current solution from this current feasible set. Okay, and you are kind of adjusting the feasible set by taking the ellipsoid, and the feasible set is given by the ellipsoid you are creating, and also the positive semi-definite cone. So as long as you can work with positive semi-definite cone, then you can impose this condition. Okay, and there's a way of working over positive semi-definite cone. Okay, that's how the ellipsoid algorithm works, and also the interior point method can also deal with this positive semi-definite cone. Yeah, so essentially, like you can just give you more information. X is PSD if and only if for all V transpose X V non-negative, which is equivalent to the trace of X times V transpose is non-negative. Okay, so if you look at this trace operator, that's the inner product defined for positive semi-definite cone, like we define inner product of two vectors in Euclidean space. So if you take this thing, this will be a cutting plane. So if your matrix X is not positive semi-definite, then you can find a vector V whose product is negative. Then what you do is you add this cutting plane that you found this vector, and then you add that condition V transpose X V non-negative. That will be a cutting plane, and you kind of repeatedly do this. That's how you do. Okay, so there's no algebraic kind of easy algebraic rules for deciding whether X is positive semi-definite, but kind of separation over the set can be done. That's my explanation. Any other question? Yeah. Which constraint? Ah, well, I mean, you just had this additional rank 1 constraint, and I just removed it. Okay. All right, so I can explain the algorithm now. So we solve the relaxation and we get on optimal solution X star. Okay. At least I know that it's diagonal entries are one and it's positive semi-definite. And because it's positive semi-definite, you can apply the classical decomposition, saying that this X star can be written as a squared of two matrices, and the if you collect the columns of this matrix Y, they are unit vectors. That's what you can prove. Okay, so you just apply the classical decomposition. Next star is given by the product of Y and itself. And because the diagonal entries of X star are one, you know that the columns are unit vectors. Okay. I have just applied this, the fact that X star is positive semi-definite and its diagonal entries are one. Then, now what I will do is to take a unit vector G, okay, from this unit sphere, uniformly at random. Okay. Then let me give you this pictorial description of what's going on. So here, because Y vectors are unit vectors, so they are somehow kind of located in in an arbitrary fashion on this sphere. And I have also picked random direction. And then if you take this G and the corresponding hyperplane defined by G transpose Y equals 0, then it gives you some random hyperplane. Okay. This is the picture of what's going on. And what you take is that some vectors lie above this hyperplane and others are not. So that actually gives you natural partition. So you collect the first set as the set of vertices whose corresponding Y vectors are staying above this hyperplane, and take the others. Okay, and this is the algorithm basically. Okay. Okay. Again, I have solved this semi-definite program, which is a continuous optimization problem, and I got this optimal solution X star, and I have applied this kind of somehow rounding scheme, okay, or some randomized procedure to construct a partition. And in fact, this partition guarantees 0.87 approximation for max cut. Okay. And let me give a proof for this. So again, the expected number of edges in this partition, okay, by the linearity of expectation, it can be decomposed into the cases for this distinct edges. Now you focus on a single edge UV. Okay. Now you compute the probability of this edge UV, belongs to this partition. Okay. That's equal to the probability that one vertex, one vector, lies above this hyperplane and the other is not. Okay. And that's essentially this expression. Now, what is the probability? Well, so now you focus on these two vectors, yu and yv. Okay. Because you're taking two vectors, they lie in the same two-dimensional space. Okay. So essentially, you take a slice of that large sphere, and you have these two vectors, yu and yv, and the hyperplane kind of cleft to this, one-dimensional line in this two-dimensional space. And because, you are taking this, random hyperplane direction for the higher dimensional space, this will also give you a random hyperplane in this two-dimensional space uniformly at random. And now this probability is equal to the probability of these two vectors being separated by this hyperplane. Okay, and that's equal to theta divided by pi. Okay, so theta uv is the angle between these two vectors. Okay, and in fact, the probability is 2 theta divided by 2 pi. The entire angle is 2 pi, but I guess you can kind of rotate this thing, but you can kind of yeah. So this is the probability. That means that the expected number of edges in this random partition is equal to the summation of the angles divided by pi. Okay, so this is the exact expression for the quantity that we are producing. Now the question is, can you compare this value with the maximum number of edges in a cut? That's what we do. So let's look at this inequality. So the optimal value, which is essentially the maximum number of edges in a cut. Now you can compare this value against this expression, which is essentially the optimal value of semi-definite programming relaxation that we have. Okay, we have this inequality because the SDP is a relaxation of the original max cut formulation. So we have removed the constraint, and this procedure will only increase the objective value. Okay, that's how we get this inequality. Okay, and x star uv equals yu transpose yv due to the Kolesky decomposition. Okay, and yu transpose yv, we know that these yu and yv vectors are unit vectors. So the inner product is the cosine of the angle between them. Okay, and you can argue that so forget about this thing. We have this expression here. This thing times 0.87 and so forth can be bounded above by theta divided by pi. Okay, I'm not going to prove it, but you can argue this. Then if you use this lemma, you obtain the fact that this is bounded above by 0.87856 times sum of theta uv divided by pi, which is essentially this expression. So this is equal to 0.87. Am I correct? Oh, no, 1 times expectation. So that means that the expectation is 0.87856 times the optimal value. Any question? Yeah. So I'm not so sure about that. Well, I guess whether I'm not aware of how to de-randomize this thing. I guess you can search for that result now. I think yeah, I don't yeah. I'll get back to you later. Okay. Yeah. Yeah, as long as your matrix is I think positive semi-definite. Yeah. Yeah. So x star, right. So what is X star? It is an optimal solution to your SDP relaxation. And so what it means is that X star is an optimal solution to this problem. As it's a feasible solution, which means that it satisfies its constraints. One of them is that the matrix is being positive semi-definite. So if you compute an optimal solution X star, that has to be positive semi-definite. Pardon? Well, X star. So you know that X star is positive semi-definite, right? Right. So what the classical decomposition says is that as long as your matrix is PSD, it can be written as a square of the same matrix. That's what it means. Okay. Does this answer your question? Okay. Yeah. Any other question?
Can I ask a question?
Yeah.
So can you go through the again, so why the probability is equal to the theta divided by pi?
Okay. So again, this probability, okay, one edge, the probability that this HUV is a cut edge is by the design of our algorithm is equal to the probability that these two vectors yu and yv are separated. Okay, so we have this expression, and these two vectors are separated in this n-dimensional sphere, right? That is this probability. Okay, and I know that this hyperplane, which is supposed to be a separating hyperplane, the direction is sampled uniformly at random, okay, from the n-dimensional space. But what I do is to focus on the two-dimensional kind of plane spanned by these two vectors yu and yv. Although yu and yv are some vectors in a multi-dimensional space, but I just focus on the slice that's spanned by these two vectors, which is essentially this figure. Okay? Because you're taking two vectors, it spans a two-dimensional space. And now you look at the image or projection of the hyperplane on this two-dimensional space. Okay, and so you have kind of many ways of getting this higher dimensional kind of n-dimensional hyperplane, but each of them gives you this projection. Okay, then what is the probability of so what is this projection? If you just focus on this two-dimensional space, it's also the direction. It's kind of like you sample this direction uniformly at random from this two-dimensional space. Okay, now you rotate this hyperplane, and if you end up this blue one, then this blue hyperplane doesn't separate these two vectors, right? So essentially, like how you separate whether this hyperplane separates these two vectors is determined by the angle between them. Okay, so if this hyperplane belongs to this theta angle, then you get a separation. Otherwise, you don't. Okay, and that's how you get this expression theta divided by pi. Okay. Yeah. Any other questions? Okay. Let me move on. And so, yeah. Did I say that it is a tight approximation? So it's known to be tight in the sense that you cannot improve this ratio unless there's some conjecture called the unit game conjecture, which is kind of remains difficult to solve. So next, unless unit game conjecture is true, you cannot improve this ratio. That is a known result. Okay, so in the sense that so subject to this conjecture being true, the approximation ratio is tight. Okay. All right, so we talked about this max cut problem, and we gave this semi-definite programming based approximation algorithm. And in fact, what I will show you now is that the same algorithm can be applied to a more general class of problems where you have a semi-definite matrix Q and you are maximizing this quadratic objective with a positive semi-definite coefficient matrix over the set of binary vectors. Okay? When you have a positive semi-definite coefficient matrix Q for quadratic, the quadratic function is known to be a convex function. And that's why we name this problem as binary convex quadratic maximization. Okay? And in fact, max cut is a special class of this problem. Why is that? Well, you take this something called Laplacian matrix of this given graph, which is defined as follows. So the diagonal entries corresponding to a specific vertex is the degree for that vertex. And if two vertices I and j are adjacent, then it gets value -1 and 0 otherwise. And this is some Laplacian matrix. And now if you take the X transpose LX, you get that summation of for the diagonal entries, you get degree I times xi squared. Okay, so X transpose LX, now you have minus summation I from 1 to n for each j such that ij is an edge. You have xi, xj, and because of this entries -1. Okay, and right, and this is equal to each ij in E xi squared plus xj squared. Now let's compare this sum with this yeah, is it? And minus 2 times summation of ij in E xi xj. Okay, and this is equal to so these values xi squared is 1 and xj squared is 1, so this is 2. So this is equal to 2 times summation over edges 1 minus xi xj. So essentially this is the 4 times if you remember the objective for max cut, it was 1/2 times 1 minus xu xv. So if you take this graph Laplacian, it is 4 times the objective for max cut. So and it is known that the Laplacian matrix is positive semi-definite. And so the max cut problem is essentially 1/4 times this x transpose Lx over the set of binary vectors. So, and we have argued that if you run the semi-definite SDP-based algorithm, you get on 0.878 approximation. And in fact, the same algorithm can solve binary convex quadratic maximization, where you can have a general PSD matrix for the objective. Any question? So again, getting back to the more general problem class, let's take this equivalent formulation in terms of this matrix variables. Now you can take out this rank 1 constraint, and you again get semi-definite programming relaxation. Now you run the same algorithm. So essentially, you solve the SDP relaxation without the rank 1 constraint, and you get this matrix X star. Now you can apply the Pulaski decomposition, and you take columns of this matrix Y, and they are unit vectors. And you take a random direction, and you take the separation. Okay. So I've said you xi equals sign. So if G transpose yi is non-negative, you get +1. If it's negative, then you get -1. That's just the same as take this set of edges, vertices for the vectors that are lying above the hyperplane. But right now we are looking at this binary problem, so I need to assign values for the variables. That's why I take this thing. But essentially, we are applying the same algorithm. Okay. Then this algorithm will guarantee that the objective is at least 2/pi fraction of the optimal value in expectation. Okay, this value is I think it's around 0.63 or something. This value is smaller than 0.87, but at least it's will give you on constant approximation guarantee. So let me give a proof for this. So because we are applying the same algorithm, we can recycle the same analysis up to this part. Okay, what we proved for the analysis of max cut algorithm, we essentially argue that this number on the left hand side, that was essentially the probability that this HUV belongs to a cut or not. Okay, it has value 1 if it belongs to the cut, and 0 otherwise. And that is equivalent to this fraction theta ij divided by pi, where theta ij is the angle between these two vectors. Okay. Then expectation of the objective x transpose qx is equal to summation I from 1 to n, j from 1 to n, qij times expectation of xi xj. And this is equal to summation I from 1 to n, j from 1 to n, qij I think this is 1 minus 2 theta ij over pi. Okay. And this is equal to I from 1 to n, j from 1 to n, qij, 1 minus 2 over pi. So theta ij is the angle between two vectors. And in other words, if you take the inner product and the inner product gives you the cosine of theta ij. So theta ij is inverse cosine of the inner product. So this is arc cosine of yi transpose yj. Okay. And yi transpose yj is equal to x star ij, okay, by the Klasky decomposition. And it's equal to I from 1 to j from 1 to n, qij. So this expression here, 1 minus pi over 2 arc cosine, is equal to pi over 2 times arc sine. Okay. So pi over 2 arc sine x star ij. Okay, so let me write down what we have. Expectation of x transpose qx is at least or equal to pi over 2 summation I from 1 to n, j from 1 to n, qij times arc sine x star ij. Okay. And now you are looking at this matrix arc sine x star. So essentially, arc sine of x star was our n by n matrix. And the meaning of taking this arc sine in front of it is that you are replacing the entries by arc sine of x star ij. Okay. So arc sine x star 1, 1, all the way up to arc sine x star n, n. And, the arc sine is some function that we understand pretty well. Now you can apply the, Taylor approximation. And then you can argue that arc sine, so you can basically expand each entry and compare it against x star ij. Okay, then you can argue that arc sine x star minus x star is positive semi-definite. I'm skipping this detail, but this is something that can be argued using some calculus rules. Okay. Now I need to use the fact that the matrix Q is positive semi-definite now. Okay. So Q times summation I from 1 to n, summation j from 1 to n, qij arc sine x star ij. So this is essentially the trace of q times x star. Or not x star, arc sine x star. Okay. And note that trace of Q times arc sine x star minus x star is non-negative because these two matrices are both PSD. Okay. So what it means is that this thing is at least trace of Q times x star. And this is essentially the optimal value of SDP. Okay. And the optimal value of SDP is at least the optimal value of the binary problem before taking out the rank 1 constraint. And that's why we get pi over 2 approximation ratio. So this is the end of the proof. So I guess we stop here, and if you have any questions, you can ask during the break.